So we had better luck today. The computer actually connected to the projector, that's good. But anyway, shouldn't change things. And hopefully it wouldn't drop off. Okay, so yesterday I talked about kind of, really basic Freeman and Metro Robertson Walker cosmology. And what I want to do today is to kind of extend this picture to describe the very first moments of the universe, out of the Big Bang. So I call it a hot universe because it's basically, the subject dealing with the universe at times when its temperature was very high. And so we're looking at, these really early times here. So now we all believe that, the universe was a very hot and dense place. We all know that. And that's basically a consequence of the fact that, we have this expanding space picture. So if you turn the clock backwards in time towards very early times, then the immediate conclusion you would come to is that the universe was basically, very dense, smaller, everything was very dense. And you also had, redshifting of the momenta, so that at early times, everything was just a lot more energetic. Okay, so it was very hot and very dense, which also means that if you have a lot of particles that are densely packed, and they're very energetic, then they can be scattering off each other very often. You could also have other processes or like decay, annihilation, whatever. Now, of course, exactly what sort of particle interaction that you would have depends on the particle physics theory that you want to embed in this picture. Okay, you embed the standard model, you have some predictions, or you have some other theories, then you would have other interactions. But there's one important thing in this entire discussion, and that is we always look at the interaction rate per particle, which is usually denoted gamma int for interaction. And we also look at the Hubble expansion rate, so how fast space is expanding. And the idea is that if you have this gamma int being much larger than h, then you can say that the interaction process that gives rise to this gamma int will be in a state of equilibrium. Okay, so this is like the one central thing that we always ask ourselves when we look at an interaction, is it happening so frequently so that the rate exceeds the Hubble expansion rate, or vice versa? Okay. Now, roughly speaking, what this means is that if you have a large interaction rate, then your particles will manage to find each other before space has time to expand. Okay, so that's why we do this comparison between the interaction rate per particle and the expansion rate. So here's a classic example of how we apply this argument of gamma int versus h. So let's say that's the concerns a weak interaction. That's the classic example, which I'm sure you've all seen. And basically it goes like this. Let's say you have a gas of ultra-relativistic particles with some temperature T. Okay? So I can estimate this weak interaction rate per particle, gamma int. Now, clearly you're looking at interaction per particle, so that would depend on the cross-section of that interaction. So that's denoted here in sigma. Okay, so cross-section for weak interaction will go like GF squared, it's weak, so Fermi constant square. And then just on dimensional grounds, you can just put T squared there to complete the expression. V here is the relative velocity between particles. And here, since I'm dealing with an ultra-relativistic gas, I can just put in V is equal to 1 in units of C. Okay. Now, last but not least, you have one particle that is scattering, and how often it scatters will naturally depend on how many scattering centers there are for it to scatter off, and that is here encoded in N. Okay, that's the number density of scattering centers for this one, I don't know, neutrino or whatever that could be scattering. And dimensionally, you can just, it's 1 on volume. So on dimensional grounds, you can just put in T cubed, temperature cubed. Okay? So once you put all of these pieces together, what you find is an interaction rate that per particle that goes like GF squared, temperature raised to the power 5. Okay? So that's a quick estimate of the interaction rate per particle. Now, we also have the Hubble expansion rate, of course. And as we saw yesterday, the Hubble expansion rate is something that depends on the sum of the energy density of stuff that I have in the universe. So that's basically the Freeman equation that we're talking about. Okay? So it's here, you have h, it's equal to square root of the sum over all the energy densities You might recall that in the original Freeman equation, there was also a term that is proportional to k, that's the curvature parameter. But normally, if you go back in a sufficiently far early enough time, the energy densities will be so large that it will dominate over the curvature anyway, if we take the present constraints on the curvature parameter from various observations. So we're just left with this, okay, just the sum over energy densities, 8 pi g divided by 3. And again, the energy density, if everything is ultra-relativistic, then it will go like t to the fourth. So after you take the square root, you end up with t squared. And g here is the gravitational constant, which we can also re-express in terms of the Planck mass. Okay, so in the end, you end up with this rather simple expression for the Hubble expansion rate. So it goes like the temperature divided by the Planck mass. Okay, so now that we have these two quantities together and we know what the numerical values for the Fermi constant and the Planck mass are, we can just basically combine these two things, take the ratio of gamma int to h, and what you find immediately is that this has this following dependence on the temperature as well as these various constants. And in sticking the numbers, what you'll find is, in the end, something like this. So we'll go like, this ratio here goes like temperature cubed, and this temperature here has to be expressed in units of MeV. So what does it mean? Well, as I said in the previous slide, we are interested in this ratio because when this ratio is larger than 1, we can say that these interactions are in a state of equilibrium. Okay? So what this ratio and what this expression here tells me, therefore, is that the weak interactions are in equilibrium if you go to temperatures above 1 MeV. Okay? Conversely, if gamma int divided by h is very tiny, okay, much smaller than 1, then you will be looking at weak interactions being out of equilibrium, and that would correspond, that would be attained at temperatures that are much lower than 1 MeV. Okay, so that's the classic example that everyone shows when they discuss gamma int and h. And just to put things in a context, we saw this picture yesterday, basically illustrating the standard standard expansion history of the universe and where everything dominated, etc. And if we look at just what we did in the previous slide with the weak interactions, then what we will conclude is that if you are looking at a scale factor that is smaller than about, say, 10 to the minus 9, then the weak interactions will be in a state of equilibrium. Okay, so this is way before BBN, last scattering surface, and structure formation. It's very early times. Okay, so what's so cool about equilibrium thermodynamics? Well, if we're looking at the ideal gas limit, and when an interaction is in a state of equilibrium, then it turns out that all the participating particles will have a phase-space distribution that is described by one of the equilibrium forms. Okay, so what that means is that you will write down a phase-space distribution, which is normally called f. It's a function of momentum, should be a function of time as well, of course. But it will take this simple form, where you have 1 divided by its exponential, E here is the energy, okay, for whatever momentum you have, and the mu parameter here is called the chemical potential, and T is the temperature. Now down here you have a choice of plus or minus 1, because it depends on whether the particle species you're trying to describe is a fermion or a boson. So if you have a fermion, then you choose the plus sign. You have a boson, you pick the minus sign. Okay, so that's an equilibrium form for particles that are kind of in an ideal gas, in the ideal gas limit. And the important thing is that if you have an interaction process and that process is in equilibrium, then all the particles that are participating in that interaction will have the same temperature. Okay, that's the zeroth law of thermodynamics, essentially. And also, the chemical potentials, the mu's here, will satisfy this relation. So you take all the particles in your initial state, you sum up all the chemical potentials, they will have to be, the chemical potentials sum here would have to be equal to the final chemical potential sum if that interaction is in equilibrium. Okay, so two things, same temperature, and this has to be satisfied. Okay, so this is the same expression again from the previous slide with this chemical potential sums. If you have elastic scattering, so a process like I plus j going to I plus j, so same same types of particles in the initial state and the final state, this condition is trivial. Okay. For an inelastic process, however, so something that you have where you have, like, for example, I plus j going to k plus l, so you have two particles in the initial state that differ from the two particles in the final state. If it's in equilibrium, then you will also have this sum being satisfied. But people tend to like to call that, give it an extra name called a chemical equilibrium. Okay? But that's just the name. It just follows from this relation up here. Now, the chemical equilibrium has, well, it's also interesting if you think about what happens if you have a particle and an antiparticle doing things like annihilation. Okay, so let's say you have a process where you have phi bar plus phi, and then it goes to maybe, I don't know, fermion, antifermion, and eventually you have gamma gamma. And if all this entire chain interaction, all these interactions are in equilibrium, then what you'll end up with, following from this chemical equilibrium law up here, is that you will have, well, mu phi plus mu phi bar. Okay, that's the initial set of particles, antiparticles. It will be equal to whatever in here, and then ultimately, because these are all in equilibrium and you have two gammas in the final state, then all of this will have to be equal to 2 times the chemical potential in the photons. Okay, and you can set it to 0. At least you can do that if you're looking at a sufficiently early times where you're still allowed to have processes that create extra photons or destroy photons in equilibrium, okay? Because the number of photons in the universe at extremely early times is not conserved. Okay, so you always have the freedom to set that to 0, in which case you can immediately arrive at this relation relating the chemical potential in the phi bar to the chemical potential in phi. Okay, so you always have this relation linking the chemical potential of the particle to the chemical potential to the antiparticle at very early times when all of this chain of processes are in equilibrium. Okay? I just note that at later times, if you go to a low redshift, when the photon number changing processes are no longer effective, you can actually end up generating a non-zero photon chemical potential, but that's pretty late times. Okay, we're talking about, well, almost CMB times actually when that happens. So for the very early universe, you can almost always assume this to be true. Okay. Right. So what about this chemical potential? What's the significance of this thing? So it turns out that when you have this nice relation linking the chemical potential in the antiparticle to be the negative of the chemical potential in the particle species, then it turns out that the difference between the number density in particles minus and the number density in antiparticles, so essentially the particle-antiparticle asymmetry, is actually related to this chemical potential parameter. Okay, so this is that's what I'm writing here. You have number density in phi, which is basically just a momentum integral over the phase space distribution in phi, and then you subtract away from that the number density in phi bar, which is basically the second part of the integral. And when you evaluate it, provided that your chemical potential is relatively small, then this is actually proportional. This difference here is actually proportional to mu phi divided by t. Okay. Now, in standard cosmology, any such asymmetry that you would have between particles and antiparticles should be of the same order of magnitude as the matter-antimatter asymmetry, which we know is tiny, 10 to the minus 10. Okay? So what this means is that this chemical potential parameter would also be quite negligible in standard cosmology. So what it means is that unless your goal is to compute the particle-antiparticle asymmetry, let's say you're working on baryogenesis or leptogenesis, then for most purposes, people tend to just set the chemical potential parameter to 0, okay? Because it's expected to be tiny in the standard case anyway. Yeah. Okay, now, So that's the chemical potential, which I will from now on set to 0. Now, if I have the phase space distribution Fp for a particle species, then it's very straightforward to find its bulk properties. So by bulk properties, I mean things like the number density of this particle species. And as I had already mentioned earlier in the last slide, essentially the number density is you can find by taking a momentum integral of this phase space distribution. Okay, so just d3p, integrate, and you have these prefactors out the front here. G alpha is called an internal degree of freedom. So essentially it's just number of spin or helicity states that your particles might have. So photons, you have 2 polarization states. So the internal degree of freedom is 2. Okay, for electrons, positrons, the equivalent internal degree of freedom would be 4 because you could have, well, electron, positron, spin up, spin down. Essentially, it's 4 of them altogether. That's the number density. And the energy density is constructed in this way. So you take, again, the phase space distribution, you weigh it by the energy per a momentum state, and then again, you integrate this thing. Okay, so very similar to the number density integral, save for the extra appearance of this energy here in the integral. Pressure, again, that's something that comes from thermodynamics. That's your integral. You take your phase space distribution and you weigh it by the momentum square divided by 3 times the energy. Okay? So these are the 3 things that you will come across a lot in these early universe calculations. Okay? Number density, energy density, and pressure. Now, I'm not going to say much more about number density and pressure, but let's just zoom in on the energy density, which is boxed up here in green. Now, so we have, in general, your phase space distribution could be anything. In equilibrium, you could assume an equilibrium form, such as what I showed you in the previous slide, so either the Fermi-Dirac distribution or the Bose-Einstein distribution. But even then, these are quite difficult to, well, actually, it's impossible to find analytical solutions. But we can take limits, okay, and ask what we get if we go to the ultra-relativistic limit. Okay, so let's say I'm looking at a temperature which is much larger than the rest mass of the particle species I'm interested in. Okay, in that case, this integral does have a fairly simple analytical form, and it turns out that this thing here will go like T to the 4, okay, temperature to the 4th. Regardless of whether you're looking at bosons or fermions. The difference between fermions and bosons would essentially come in through the prefactors. Okay, so you have T to the 4th in the ultra-relativistic limit. On the other hand, if I take the non-relativistic limit, okay, so if I look at the case where the temperature of the bath is much less than the rest mass of the particle species, and then I take this expression and then evaluate it again analytically in that limit, what I'll find is a very different behavior. I'll find something like this, okay? So you have these M's here, which basically gives you the right dimensions. And most importantly, you have this exponential suppression. You have E raised to the minus M divided by T. This is called Boltzmann factor, and obviously if I'm looking at the non-relativistic limit where M is larger than T, then we're looking at an exponent of a negative large number, okay? So this tells you immediately that this energy density here in the non-relativistic limit is highly suppressed. So people like to call it Boltzmann suppression sometimes. Okay, so this is it's basically this exponent that's suppressing the energy density in the non-relativistic limit. Okay, so you have these 2 limiting behaviors. That's good. Now, so what's the significance of that? Well, the significance of that is if I now go back to the Freeman equation, okay, which relates the Hubble expansion rate, h squared, to the sum of all the energy densities that I have in the universe, then what this calculation, rough calculation of the energy density tells us is that this energy density sum here would be completely dominated by stuff that is ultra-relativistic. Okay, because those ones go like T to the fourth in the energy density, whereas everything non-relativistic is highly suppressed. Okay, so this is entirely dominated by relativistic stuff. And what's common for us to do is to rewrite this sum over here in terms of a G star parameter, okay, which is highlighted in red over here. It's generally a function of the temperature. And the G star parameter is defined so that I have basically, okay, a bunch of things over here, prefactors, 8 pi g divided by 3, some prefactors coming from evaluation of these integrals. G star is here, and I also factor out this T gamma to the fourth dependence, which is what you expect anyway when things are ultra-relativistic. Okay? So that's how G star is defined. Now, as said before, G star is a temperature-dependent function, okay, because depending on what temperatures you're looking at, different particle species could be ultra-relativistic or non-relativistic. Okay, that's why it's a function of time. It's also a function that is specific to the particle physics theory that you have in mind. So here is a picture of G star of the standard model. Okay. So what I have here on the horizontal is temperature. So temperature increases this way, which means time goes this way. Okay, can you see the red? Goes this way. Okay. And this here is G star. Okay. And the black line here shows you how G star evolves. And as you can see, you start off pretty large, with a pretty large G star, which is about 100. And that is because you take the entire particle standard model spectrum, and if you go to a temperature that is, 10 to the 6 MeV, okay? That's a pretty large temperature, and all your standard model particles would be ultra-relativistic, okay? So which is why you have 106.7 up here, which is a pretty large number. But as you evolve forward in time, and the universe expands and it cools, the temperature also drops. Okay, so as you can see, the black line here slowly drops off. And up to here, you have TT bar going at non-relativistic, and so it drops down to 96.25, and then at around these scales here, W's and Z's and everything also goes to non-relativistic, so your black curve drops down again, so on and so forth. And up to this point here, you have this really sharp drop off, this cliff over here. And that is because this place here corresponds to the quark-hadron phase transition. Okay, so in other words, at higher temperatures than about 200 MeV or so, you essentially have a quark-gluon plasma here in the universe, and then you hit QCD phase transition, and everything becomes confined into hadrons, and they are massive. Okay, they're quite massive relative to the temperatures we're considering. So you suddenly have this cliff here, G star drops off. Okay, and you keep moving forward. Pions become non-relativistic at this point, muons as well, and then you have another sharp drop off over here, which corresponds to the final annihilation of E plus and E minus. And so in the end, once you go to very late times, the G star value that you left off with is just 3.38. Okay, so you started at 100, you end up with about 3. Okay. What's there? What's left? Well, what's left here are mainly photons and neutrinos. Okay, the photons can't annihilate anymore; they're massless. The neutrinos are also not going anywhere. Okay, so that's what we expect to be left in the universe today. Everything else would have decayed away, or their abundances would be highly suppressed. Okay. Yep. Yep, that's a very good point, which I'll get to in a bit. So we're just looking at the black line for now. That's a G star. Okay. I also want to highlight that there are small amounts of electrons and nucleons and nuclei. Of course, that's what we are made of. So something has to be left behind to form us. But as I said, they're small, and small in this context means 10 to the minus 9 times the number density of photons. There should, of course, also be dark matter, right? But okay, it would also be in this picture, but it would also be a small amount, at least at these high temperatures. Okay, cool. Now, another important concept, and it is related to the dotted line, is that of entropy. Okay, and so far we talked about just pressure and energy density, but you can also form a entropy parameter called S. Okay, and essentially what you do is that you take the energy density, you add to that the pressure and divide it by temperature. That's the entropy density. And what's important about this parameter is that if I imagine a universe that is just slowly expanding, so that at every stage you maintain a kind of quasi-static equilibrium, then you are in a maximal entropy state anyway, because that's what equilibrium is, and you maintain equilibrium at all times. So what this means is that the co-moving entropy density, small s, okay, which I form by multiplying the large S by a cubed, is actually approximately conserved. Okay, so you're always in equilibrium, you don't create entropy, the only thing that's happening is expansion of space, so the co-moving entropy density as a result is the same everywhere. So here's a little cartoon illustrating what's happening. You have small s in this, between these co-moving observers, it's always the same, small s, if everything is expanding in this quasi-static way and equilibrium is maintained. Now, so that's the entropy density. And earlier we defined the G star parameter, right? And as I mentioned, the G star parameter is completely dominated by ultra-relativistic stuff. Well, for the entropy density, you can also define an equivalent concept, and that's called G star S. Okay, so this is the entropy degrees of freedom, as opposed to the energy density degree of freedom that we had earlier. So this is G star S, and again, it's a temperature-dependent function, and again, it's dominated by relativistic species. It is also specific to a particle physics theory. And the important thing, however, is that in general, G star S, which is based on entropy, is not the same as the energy density degree of freedom. And that is because by defining things in this way, you have essentially a T cubed dependence on the temperature. And if my particle species, if I have multiple particle species in the universe and they have different temperatures, then this different temperature dependence, EQ versus E4, will actually lead to the G star S and the G star being different. And that's really the reason why it is that you have this deviation between the solid black line, and the dotted line. Okay, the solid black line here is G star, so based on the energy density of the stuff that you have in the universe, whereas the dotted line here comes from looking at the entropy in the system. Okay? Now, so that's what G star S. It's different from G star in general. Often they are the same, but sometimes they're different. And as I said in the first slide, and the slide before, there is the concept of co-moving entropy conservation. Okay, so if you have, expanding in a universe is expanding in a quasi-static way, the co-moving entropy is conserved. So what I can write immediately is that this S, the co-moving entropy density, is a constant. And since S is given by this bunch of stuff, okay, you have G star and then T gamma and then the A cube and some prefactors, then all of this has to be a constant, right? So I can immediately rearrange to solve for the evolution of T gamma, so the temperature of the photons, as a function of the scale factor. And what I find is that this temperature here for the photons will be proportional to G star S raised to the minus 1/3, and then the scale factor to the minus 1. Okay? So naively we think that the temperature should scale like a to the minus 1, but that is not completely true. There's also a dependence on entropy. So if entropy is, if the entropy degrees of freedom is different at different times, that would influence how the photon temperature evolves. Now, there's a classic calculation using this temperature relation, and that is the neutrino to photon temperature ratio. Okay, and so this is a schematic outlining what's roughly happening. So basically, we're looking at an epoch in time when the temperature of the plasma is about, say, 1 MeV or so. Okay, and the importance of this is that at 1 MeV temperature, 1 MeV, that corresponds to weak interactions going out of equilibrium. Okay, which we did a few slides ago. So that's also the time when the neutrinos, which only have weak interactions, lose contact with everything else in the universe. So we call that neutrino decoupling, because the neutrinos are not talking to anyone anymore. And that happens at a temperature of about 1 MeV. Now, if I ask, and if I ask myself what kind of stuff I have in the universe at 1 MeV, then clearly I'll have a QED plasma, which would contain positrons and electrons, and there will also be photons. And I will also have 3 families of neutrinos and antineutrinos. Okay? Now, at these fairly early times, because you have weak interactions being in a state of equilibrium, you can expect the QED plasma to have the same temperature as the neutrinos. Okay, so what I can do immediately is to try to calculate the G star S for the universe at these early times at 1 MeV. Okay, so I will have G star S, I will have a contribution from the photons, G gamma, so G gamma is 2. And then I have GE, which is the for the electrons, so G gamma is 2, GE is 4 for electrons, positrons, and G neutrinos is also 2. Okay, that is because you can talk about Dirac versus Majorana neutrinos, but the weak interactions only care about left-handed neutrinos and right-handed antineutrinos. So in the end, G nu is just 2. And the factor 7/8 here is really just something that's related to the Fermi-Dirac distribution. Okay. So that's what we have. And if you combine all the numbers together, what you get is that G star S at early times is about 10.75. Okay. Now, okay. So now I move forward. So that's the first, what happens to G star at about 1 MeV. As I move forward in time and the temperature drops, then there's an event at temperatures around the mass of the electron, which leads to the annihilation of E plus and E minus. Okay, so your temperature is low enough, your electron mass is large relative to the photons, and then you have basically E plus and E minus going into photons one way, and you cannot have gamma gamma going back to E plus E minus because the photons are not sufficiently energetic. Okay, so that happens around here. And if you keep moving forward in time, what you'll find is that at a sufficiently late time, the universe will be depleted of electrons and positrons because they have annihilated away. Okay? But what has happened is that you have essentially dumped all the energies all the energy that is initially in the positrons and the electrons into photons. So you're kind of reheating, if you like, the photons. Okay? So generally what you would expect is that the photon temperature you would attain after this E plus E minus annihilation to be larger than the temperature in the neutrino sector, which are already decoupled. Okay? So again, I can calculate the G star S in this later time, and what I find here is that, well, the expression looks kind of like what I had before. I still have the G gamma, because I still have photons around, but now the E plus E minus have gone. I don't have to worry about their contribution anymore. They're gone. Okay? Then I have the neutrinos as well. I have 3 species of neutrinos times the internal degree of freedom, which is G nu equals to 2. 7/8 is this Fermi-Dirac factor. And now I have to also include the fact that my neutrinos are a little bit cooler than the photons. Okay? Therefore, I have this T nu 2 divided by T gamma 2 raised to the power 3 factor account for the fact that the neutrinos are a little bit cooler. Okay? Now, having written these 2 things down, what I can now do is to apply the expression we saw in the previous slide for the for the photon temperature, so this one, here, this one, in order to write down this expression here in the first box. Okay, so this tells me how the temperature of the photons at the later time relates to the temperature of the photons at an earlier time. Okay, so you have G star S1 divided by G star S2 raised to the 1/3, and then you have the two scale factors A1 and A2. That's just applying that previous expression. Now, I can also ask, how does the temperature of the neutrinos evolve across E plus E minus annihilation? Well, if the neutrinos are decoupled already from the plasma, okay, then it will not partake in the energy that is dumped into the photon bath through E plus E minus annihilation. Okay, so the only way the neutrino temperature can evolve is really just through the simple process of redshifting. Okay, so I would expect the neutrino temperature at the later time to be smaller than the neutrino temperature at the earlier time, basically by an amount proportional to the scale factor ratio, A1 divided by A2. Okay, so now I have an expression for the photon temperature and an expression for the neutrino temperature. The next thing I can do is just to divide them through. Okay, so I form the ratio T nu2 divided by T gamma 2. Okay, and I note that when I do that, I will have, well, I'll still have T nu T gamma, and then I will have T nu, so 2 T nu 1, T nu 2, and then I have these G star factors. One-third. The scale factors will cancel out. And the last thing I need to do is to recognize that, so this is gamma, is to recognize that T nu 1 and T gamma 1 at the earlier time, okay, where we have the neutrino temperature being the same as the photon temperature. So this thing here is just 1. Okay, so I'm just left with a very simple expression for the neutrino to photon temperature, which is just proportional to G star S at the later time divided by G star S at the earlier time raised to the 1/3. And when you evaluate that numerically, you'll end up with this famous expression of 4 divided by 11 raised to the 1/3 for the neutrino to photon temperature. Yes?
Could you explain again why EU2 doesn't care about the ratio of G stars?
That's because the neutrino decouples at a temperature of about 1 MeV. So after decoupling, it just doesn't talk to anyone anymore. So the electrons and the positrons can do whatever they like with the photons, and the neutrinos wouldn't know about it. So they will just keep evolving, and the only thing that can affect their evolution is redshift. Okay? So that's another classic example of how you use entropy conservation in the early universe to figure out things for you. Okay, so that's the neutrino temperature. Okay. Oh, everything okay so far, or anyone needs to ask anything, clarify anything? No. Okay. So far I've said everything I've said concerns what happens when you have a state of equilibrium. But as the universe expands and things cool down, at some point we generally would expect things to go out of equilibrium. We'd expect an interaction rate per particle to drop significantly below the expansion rate, okay, once we go far enough in time. Okay, so in other words, at a late enough time, you would often find interaction rates being much less than the Hubble expansion rate, okay? So what this means is that when this condition is attained, then the interaction that is under consideration will no longer be able to change either the energy density or the number density of the participating particles. And that interaction is out of equilibrium. So what do we do when things go out of equilibrium? Well, actually, before I get to that, let me just also define a couple of terms. So you probably heard about the word decoupling. Actually, I said it myself just 5 minutes ago. There's also a term freeze out. So you heard about freeze out if you do Wim dark matter. So these two terms here have something to do with things going out of equilibrium, but they actually mean slightly different things. Okay, so you're going to be careful about which one you mean. Decoupling means a particle species completely decouples and does have no thermal contact with anything else in the universe. Okay? In other words, all of its interactions with other particle species will have to be out of equilibrium. Okay? When that is attained, that the particle species concerned is decoupled. Okay? So that's what happens to neutrinos at 1 MeV or so. All the weak interactions switch off, and then that's it. The neutrinos don't talk to anyone anymore. Freeze out is a bit different because freeze out only concerns number changing interactions. Okay, so primarily we're talking about things like annihilation or pair production, anything that changes inelastic processes that can change the number density of a particle species. And when those processes, those number changing processes stop being efficient, then what you have is a freeze out of the number density, the co-moving number density of the particle species. Okay? So those things go out of equilibrium, those number changing processes go out of equilibrium, you have a freeze out. But you could still have elastic scattering processes that keep the particle species talking somehow to the surrounding, to other particle species. Okay, so it's not decoupled, it's only frozen out. So they're slightly different things. Okay? Yet another word that you may have heard of is freeze in. And essentially the idea is that you may have some beyond the standard model process, some theory that gives rise to an interaction where the interaction rate, so per particle, so gamma int, never quite reaches the state of gamma int being much larger than h. Okay? So this condition it's fine for the standard model, but you could have a BSM model where this condition is never really completely reached. But you may have gamma int being kind of close to h, or maybe a little bit below, so that you still produce some BSM particle species in a kind of a trickle. Okay? And then eventually you make a sufficiently large population. But that's called freezing. So you make a little bit at a time and then you populate. Okay? Rather than the other way around where you start with equilibrium and then you freeze out. Okay, so this is called freeze-in. This is all I will say about freeze-out and freeze-in because you will hear more about dark matter production mechanism next week anyway, so I'll let Torsten tell you more about freeze-in and freeze-out. Okay, now, so these are just some generic terms that we use to describe how things go out of equilibrium. And now I'm going to say a few more words about how you would actually track a process going out of equilibrium. Okay? And the way we do that is basically to use the Boltzmann equation. Okay? The simplest way to do that is to use the Boltzmann equation. And here is the Boltzmann equation in the most general form I can find. And F here, F1 here is a one particle phase space density, so missing word, of particle species 1. Okay? And all of this stuff over here on the left-hand side is called the Liouville operator. And you have on the, here you see, okay, df1 dx alpha, this is in covariant notation, so P here is the form momentum. This gamma here is gamma I alpha beta, that's not the same as gamma int, this is actually a bunch of Christoffel symbols, and that's basically where gravity comes into play, okay, if you're looking at a gravitational system. So if you want to describe long-range interactions, you would also introduce those interactions into the Christoffel symbols. Okay. Now on the right-hand side, you have a thing here, C of f, functional of f. This is called the collision term, and the way I've written the Boltzmann equation here is covariant form and is Lorentz invariant. So this is a Lorentz invariant collision term over here. And the one particle phase space, which I'll say more about in the next slide, but the one particle phase space density is basically defined such that the number of particles 1 in the phase space volume, and the phase space volume is dx1, dx2, dx3, dp1, dp2, dp3 is this thing. Okay, so that's a number of particles of particle species 1 in a phase space volume. Now, that's a technical definition, but let's also look at the various terms. So So I mentioned earlier that gravity goes into the Christoffel symbols, right, here. Now, fortunately, if we're looking at just a homogeneous and isotropic FRW universe, then the only thing gravity does is to cause expansion of space, okay? Doesn't do anything else. So what it means is that I can also write this Liouville operator in a simpler way if I change the dependent variables of my phase space density from this kind of, from the 4 coordinates and the 4 momentum to something simpler, okay? So instead of writing F1 is a function of x alpha and pi, I can just say, okay, I know I have a time variable that I have to deal with, so it's just time t, and I know that there's a physical momentum that I can that I need to that will redshift. Okay, so I can change instead of using the 4 momentum, I can use the physical momentum as measured by a co-moving observer as a dependent as an independent variable. Okay, so once I do that, then this Boltzmann equation actually simplifies to something that looks like this. So you have df1 dt, and then you still have this df1 dp structure, which is kind of equivalent to that. But the spatial parts drop out because we are looking at a homogeneous and isotropic universe. And all gravity does is to introduce this h factor here, which is essentially the hp here is essentially dp dt. Okay, so redshifting momentum that goes in here. Okay, and finally on the right-hand side, I still have the collision term, and I also end up getting this one on E1 over here, because if you go back, refer to the covariant form of the Boltzmann equation, you have the 4 momentum multiplying the first term. Okay, so if you wonder why it is that you write your collision integral with a 1 on E here, that's the origin. It's because that's the fundamental form of the Boltzmann equation, if you like. Okay, cool. So that's probably the phase space, the Boltzmann equation that you are probably familiar with. And lastly, I said I would say something about the collision term, CF over there on the right-hand side. And well, the form of the collision term depends on what kind of short-range interaction you're trying to describe. But here is the collision term for a generic 2-to-2 scattering process. And what you see here is basically you have 1/2 and then a bunch of phase space integrals. So this thing here is a Lorentz invariant phase space element. You have energy momentum conservation being encapsulated in this Dirac delta. You have a matrix element for the interaction you're interested in, and all of that is followed by a big bunch of phase space quantum statistical phase space factors, including quantum statistical factors like here you have 1 plus F1 or 1 minus F1, depending on whether F1 is a boson or a fermion. So if it's a fermion, you will have 1 minus F1, which corresponds to Pauli blocking. And if 1 was a boson, then this factor here would be 1 plus F1, so you have boson enhancement. Okay, so you have these quantum statistical factors for each of the particle species. Okay, so this particular collision integral is for a 2-to-2 scattering process. You could, in general, have much more complicated collision integrals if you have a more complicated kind of process. Okay. Now, so before I say more about the collision term, which I will in a bit, let me just also ask the question of what happens to the phase space F1 if the collision term is exactly 0. Okay, so if I go back here to this expression and I set the right-hand side to exactly 0. Okay, now what happens is the following. Well, if your particle species is not interacting, but space is expanding, then the only thing that can happen to your particle species is that the momentum will redshift. Nothing else will happen. They're just going along, not doing much, but the momentum would redshift with the expansion of space. Okay, so P going like a to the minus 1 is always true in an FLRW universe. So therefore, what is useful to do in the cosmology business is to define a non-redshifting momentum that is itself constant in time. Now, there are many ways to do this, but probably the correct way to do it is to just basically multiply your momentum with the scale factor. Okay, so I multiply momentum with the scale factor, and I would immediately cancel out this redshifting effect. You could also choose to normalize your momentum to the temperature, which is actually done in a lot of dark matter baryogenesis calculations. But that comes with the assumption that your temperature scales like 8⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ Okay? So, but this is true. Drawback, of course, is that Q is not dimensionless, but yeah, who cares? Okay, so now that I've defined this non-redshifting momentum Q, what it also means is that instead of writing my phase space distribution in terms of time and the physical momentum P, I can choose to describe the phase space distribution using the non-redshifting momentum instead. Okay, I can just write F1 is a function of T and Q. And that's great because then you would have, when you write down your Liouville operator, you'll have a df dt, you'll have a dq dt, and then df partial f partial q, all of this is equal to 0. But this momentum q is non-redshifting, so dq dt is equal to 0. Then your equation of motion simplifies significantly. You just have a df1 dt is equal to 0, and that's it. Okay? And this immediately tells you that the phase space density, F1, if you write it in terms of this non-redshifting momentum, must remain constant in time if there are no collisions. Okay? So you have a particle species with some initial phase space distribution. It's just going to maintain that exactly the same phase space distribution throughout all time afterwards if there are no collisions. Okay? Okay. Now, so that's what happens if you have no collisions in your for your particle species. But most of the time in early universe physics, you want to actually ask what is the consequence of a collision term. You know, what is the consequence of an interaction? Okay, so that means you have to deal with the collision term and solve it. Then the next question that you can ask is, well, if I look at the Liouville operator, obviously it depends on time and it also depends on Q, right? The momentum. And the collision integral would also be dependent on the momentum of the participating particle species. So then you can ask, okay, do I really need to follow the entire fully momentum dependent Boltzmann equation in its full glory in order to calculate anything? Well, as it turns out, sometimes you need it, sometimes you don't. Problems that do require you to check the entire full momentum distribution would include things like if you're interested in freezing, okay, you freeze in a different momenta, then you probably want to check your entire momentum distribution in a detailed way. There are those of us who like working on precision neutrino decoupling or N-effective. For that problem, you also need the full momentum distribution, primarily because you have neutrino oscillations which can generate some funny momentum-dependent effects. But actually, if you're looking at precision neutrino decoupling, you have to go to the density matrix formalism anyway, so beyond Boltzmann. Light sterile neutrino thermalization is another problem that requires a full momentum treatment. But for most things that I guess you'd be hearing about, things like WIM freeze-out, you don't really need to check the full momentum distribution. Or recombination, photon decoupling, or standard thermal leptogenesis, you don't really need to care about the full momentum distribution. So in those cases where you don't need the full momentum dependent Boltzmann equation, what you can do is to essentially integrate the momentum, integrate the Boltzmann equation in momentum in order to form an equation of motion for the number density. Okay, so what I have here is the Boltzmann equation again in black, okay, in this momentum dependent form. So you have df1 dt and then all these p's over here, and then you have the collision integral, and then you integrate on both sides of the equation over momentum. Okay, and what would happen once you do that is that this first term here would become dn1 dt. So that's basically just the rate of change of the number density of particle species 1. And the second term, which comes with this Hubble expansion rate over here, would end up being something like this. So you have 3 times h times n1, and that's basically a term that describes how the expansion of space would dilute the density of your particle species. And then on the right-hand side, you will have this integral over the collision integral. Okay? Now, this is what we would like to do, integrate over momentum to form this simpler equation. However, if you look at the right-hand side of this equation, it's still pretty ugly, because you still have to deal with this collision integral, and you still have to perform this momentum integration. But as it turns out, for a lot of applications, there are simplifying assumptions that you can put in order to turn this collision term on the right-hand side into a form that is a bit more manageable. Now, I understand that you'll hear about this next week in the dark matter lecture, so I'll just briefly outline what you need to do. So basically, what you can do is to ignore, first of all the quantum statistics factors and assume everything to take on the Maxwell-Boltzmann distribution. So in other words, you assume the equilibrium distributions to have a fairly simple form, so everything is just exponential to the minus energy divided by temperature. So once you turn things into exponentials, things simplify. Another thing you can assume is that all your particle species will have a common temperature T, which is usually quite well justified if you are interested in looking at things like freeze out, because you normally would still have elastic scattering processes that are still in a state of equilibrium that would allow you to keep everything at the same temperature. And the last assumption you can put in is that the phase space density takes a simple form like this. So you have the actual number density divided by the equilibrium number density, and this is scaled by this exponential e to the ei divided by t. Okay, so the same factor that you see over here. Okay, so once you make these assumptions, then it turns out that you can really simplify this collision integral drastically. Okay, and people do that all the time. So you end up with something like this. Okay, so for a 2-to-2 process, you end up with basically all of this. You have the cross section of the interaction. You have the equilibrium number densities for 1 and 2, and something like that. Okay? Yes?
Can you explain the approximation for the phase space?
Which approximation of the phase space?
In the previous slide.
Which one?
The phase space density as the ratio of the...
This one? Yeah. That's just an assumption people put in. You can justify it if you have a very large chemical potential. And yeah, so what you can do, okay, so one thing you can do is that you write down, say, Fermi-Dirac distribution and keep the chemical potential in there, and then you take the non-relativistic limit. That actually pops out. Yeah. Yeah. Okay, right, okay, so this is a simplified collision integral that you can write down if you make all the assumptions that I did on the previous slide. And as I said, Thorsten will tell you in detail how that works next week. And so what you see here is, as I said, you have basically these equilibrium number densities, which are things that you can pre-evaluate at different temperatures. The only real-time variables on the right-hand side here are N1, N2, and N3, and N4. Okay, and also this thing here, the sigma v in the brackets, that's a thermally averaged cross section. Okay, so again, if you look at the form of this thing, you have your usual matrix element, and it's weighted by these thermal factors. Okay, minus E1 minus E2 divided by T. And again, this thermally averaged cross section is dependent on it's a function of temperature, but it again is something you can pre-evaluate. Okay, so if you do numerical work, anything you can pre-evaluate without having to track real-time functions, it's make life a lot easier. Okay, so that's why it's quite common to see the Boltzmann equation kind of massage into this integrated form. Okay. Okay, so now. So there are several instances where you can apply this integrated Boltzmann equation. So one of them, as I've alluded to multiple times, is to compute rim freeze out. Okay, so basically, you know what a WIM is. It's a weakly interacting massive particle. It's a generic cold dark matter candidate. And you have a generic production process where essentially you have some standard model particles, let's call them X, and then X bar annihilating into 5 bar and vice versa. Okay, that's your generic production of a WIM particle. And you assume the standard model particles X to be in a state of thermal equilibrium, because the standard model particles will have other interactions with amongst themselves. Okay. Now, so that's it. We're interested in tracking the how this process go out of equilibrium, and but of course you could also expect elastic scattering processes like phi scattering of X and so on. But those things are elastic processes. They tend to stay in equilibrium for a longer time, so we don't care about those. Okay, so we're only interested in the annihilation. So what you can do then is to write down this integrated Boltzmann equation, which is basically the equation I showed you before. So you track the number density of dark matter as a function of time. Here describes the expansion of space, and then on the right-hand side you have the thermally averaged cross section for this process. You compute, and all you have to do is to stick this into your computer and solve, and then there you have it, your dark matter production, WIM freeze-out. That's a picture of a WIM freeze-out, which you've probably all seen. So what you're plotting here is X in the horizontal axis, which is usually defined as m divided by t, so time moves forward from left to right. And what I'm plotting here is the co-moving number density, so in the vertical. So what you're seeing here is basically the co-moving density of your WIMs. And so to start off with, you have a lot of them, but then as the WIM goes non-relativistic, the co-moving number density drops off, and you have annihilation, and at some point the annihilation cross-section will freeze out. So if it freezes out at this point, that's the line that would be followed by the WIM abundance. If it freezes out here, then you'll follow this line, and so on. Okay? And which line the WIM number density would follow would depend on the annihilation cross-section. So again, you'll hear more about this next week. Okay, another application of the Boltzmann equation is that of recombination. And so this is much lower energy physics. And basically, recombination concerns what happens to the formation of the CMB. Okay? So basically, the formation of the CMB comes about when you have photons that decouple from the, they stop scattering efficiently of electrons. Okay, so at high temperatures, you have Compton scattering, which allows the photons to scatter off electrons very frequently, so the universe is opaque to photons. But as you lower the temperature, at some point, you don't have enough free electrons around for the photons to scatter off, and the photons then start to free stream to infinity and be observed by us as the cosmic microwave background. Now, so the key point here in this whole photon decoupling process is that of the amount of free electrons that we have in the universe. And to determine the amount of free electrons we have in the universe, so in other words, electrons that are not bound in an atom, we need to consider how how these free electrons are bound in hydrogen or helium and not. Okay? So basically, we're looking at a process like so. Okay? So you have E plus a proton going to a hydrogen atom and a photon. Okay? So we can write down again a Boltzmann equation to track how many free electrons we have. So d and E divided by dt, and that would be given by what the abundances of the protons, the hydrogen, etc., and also the cross section at which this process happens. Okay? And the idea is that you have free electrons to begin with, and then they get combined. And if everything gets recombined, all the electrons get recombined into part of a neutral hydrogen atom. You have no free electrons around, and as said, the photons can free stream to infinity because you have no more free electrons around for Compton scattering, and we see the photons as a CMB, as the CMB. Okay, so that's all I have to say about the hot universe. And the take-home message really is just gamma versus H. That's one thing that we think about all the time in hot universe calculations. At least that's a quick rule of thumb to decide if your interaction matters or maybe it doesn't matter. And if it really matters, then you probably need to bring out your Boltzmann equation to check how the process go out of equilibrium to calculate things like the final abundance of dark matter or free electrons or other things. Okay, so that's the hot universe. I still have several slides on very kind of sketched out inflation. Do people want to hear it or not? Yes, okay, cool. Let me drink some water first. Okay, so that was a hot universe, which is basically basically standard hot Big Bang. Now I'm going to move on to say a couple of words about inflation. I'm not an inflation expert at all, so what I'm going to be telling you is basically just a very rough sketch of what inflation is about. Okay, no details. So we're looking at an epoch in the early universe that is way early. Okay, so hot is merely here. We're talking about inflation, which is even before the hot phase. Okay. Now, if you're interested in describing observations and expansion of space, BBN, whatever, then a lot of it is already consistent. I mean, this data is already quite consistent with just the standard hot Big Bang picture. But there are three puzzles that bothered people back in the 1980s a lot, or maybe even before, that are basically solved by the introduction of inflation in cosmology. So the three problems are the horizon problem, okay, the flatness problem, and the so-called relic problem. Some of these are, well, arguably philosophical, if you ask me, but maybe I shouldn't be too harsh, because actually inflation also gives us a mechanism to generate density perturbations that could be formed into galaxies, so maybe I shouldn't be so harsh. But anyway, these are the three problems that bothered people back several decades ago, and that's why they invented inflation to solve the problems. Okay, so the first one is the horizon problem. And the question they posed basically is, why is the CMB so uniform, even though it should be made up of many causally disconnected patches? Okay, so this is a CMB. Okay, there are fluctuations on it, but it looks pretty much the same everywhere you look. Now, what I mean by causally disconnected patches? So again, to understand this statement, I go back to this picture that I showed yesterday, which essentially shows us over here, and that's a photon, that's our backward light cone. So in other words, if a photon comes from the CMB last scattering surface and it travels forward in time, it moves a certain co-moving distance to get to us. Okay, so that's another light ray over here. So this is our backward light cone. Now, the CMB is somewhere back here in time, pretty early on, right? Okay, so that's a photon that would have come from the last scattering surface over here. That's another photon that would have come from the last scattering surface over here. Now, again, I can draw backward light cones for these two photons. And what I find is that instead of Big Bang, the backward light cone of this photon is tiny. Okay? This one as well. And in fact, these two backward light cones don't even overlap with each other, if I assume standard Big Bang with, radiation domination and so on and so forth. So this is problematic, because this picture here tells us that the photon over here that was emitted on the last scattering surface over here, and this photon here wouldn't have known about each other if the universe had a thermal history described by this completely standard picture. Okay? So and the question is, why is it that I still have essentially the same temperature for the CMB photons over here compared with over there, if they didn't know about each other? Okay, so that's called a horizon problem, because the horizon at the time of the CMB was too small for these two photons to have known about each other. Okay, so that's motivation one. Motivation two is the flatness problem. Now, if you recall from the Freeman equation, the Freeman equation has a dependence on the curvature parameter, and that curvature parameter has a scaling with the scale factor. It goes like 8⁻². So what this means is that if you have a tiny little bit of curvature at all, then you could actually end up blowing it up. Okay, it's possible to blow it up. Okay, so in fact, what people have calculated is that they asked, if I look at the curvature at a time 1 nanosecond after the Big Bang, okay, which is a tiny bit of curvature, what should I see today? Then it turns out that you need an extreme amount of fine-tuning at the Planck time in order for the curvature to not be observed today. Okay, so you start with non-zero curvature, your universe expands, and then today, unless you fine-tune it, you should see a huge amount of curvature, but we don't. Okay, so why is that? Okay, that's a flatness problem. The universe should not be flat, but it looks flat. It shouldn't be flat, but it does look flat, so why? What did I do? Oh, here we go. I think I just moved a bit because I was leaning on the letter. Okay, so that's the flatness problem. And the last one is called a relic problem, and it's sometimes called a monopole problem. And that comes about because you like there to be, people used to like to think about unified, theories like guts and whatever. And these gut theories would have various stages of spontaneous symmetry breaking. And every time you have a symmetry broken, you will have a topological defect coming from the symmetry breaking. So you could have monopoles that are formed as a result of the symmetry breaking. You could have strings, domain walls, and all sorts of nasty things that you don't really want to have around because we don't see them. Domain walls in particular are pretty dangerous. It will cause a huge amount of accelerated expansion, which we don't like. Okay, so again, we have to explain these things away. Why we don't see them if gut theories are true. Okay. The simple solution is just to say guts is not true, but or you can find a solution. Okay. Anyway, so these are the three motivations for inflation, and the inflation solution is very neat. It's very, very simple, and essentially what you do here is that you say, well, okay, I have my standard expansion history, okay, with lambda domination, matter domination, and radiation domination, and what I do is to tag another phase in the evolution history before radiation domination, okay, and that's inflation, and this is a phase that is dominated by some form of energy density that leads to an accelerated expansion. Okay, so that at the beginning of inflation, you have a scale factor at t start, which is a factor e to the minus 60, less than the scale factor at the end of inflation. Okay, so you have basically not much, suddenly expanding by a lot, and then somehow you exit back into radiation domination. And once you do that, you can solve all the problems that I talked about before. Flatness, horizon, and relic problem. And it's easy to see why this is a reasonable solution, and that is if you think about the flatness problem. So imagine that our universe is a balloon, and we are, well, this little end over here. And imagine that you suddenly blow up this balloon by a lot, exponentially by a lot. So initially, if you're at the end, you'll think, well, this balloon is curved, it looks curved to me. But if you suddenly do a exponential expansion of the balloon, then if you expand it enough, then the balloon will look flat to the end. Okay, so that's essentially the idea of why you want to have this phase of exponential expansion. Okay, so you get rid of this fine-tuning problem because your expansion will help you to fine-tune, essentially. Now, the relic problem is solved in exactly the same manner. So if you imagine again that you have monopoles and domain walls that might be dotted all over the place on the surface of the balloon, but if you blow it up again exponentially by a lot, then these monopoles and relics that you don't want around will be so diluted that you won't see them anyway. Okay? And last but not least, for the horizon problem, you solve it by inflation because essentially what you're doing is that instead of having time beginning here in the middle, you're basically tagging another, I don't know how many billion years before the nominal start of the big or radiation domination. So that's good because now you have all this time, okay, negative in these units, units, and you can see that now if I look at a photon that is being emitted on the last scattering surface over here, this is this backward light cone, okay, all the way extending all the way back in time. And similarly, this photon here would have a backward light cone that is here in this space, and now the two backward light cones overlap. Okay, so I've solved the horizon problem because now in some very, very distant past, these two photons would have known about each other. Okay, so that explains away why it is that they are allowed to have more or less the same temperature. Okay, okay. Now that's the basically the generic idea of inflation. The actual implementation of the inflationary theory usually involves some sort of scalar field. And you can make it very complicated, but essentially what you're doing here is that you say you have a scalar field, okay, which is some dynamical quantity, okay. And if I want to write down the energy density for homogeneous and isotropic real scalar field, then essentially you just have this kinetic term over here, d phi dt square 1/2, plus whatever potential that the scalar field lives in. Okay, so it's basically kinetic plus potential energy, if you like. Now, I can also calculate the pressure of this scalar field, and the scalar field pressure would be given by the same kinetic term, but minus the potential. Okay, I'm giving you this expression over here, but you can write down the Lagrangian for a scalar field, a real scalar field, and then just calculate T mu nu using this expression over here. And then you identify the time part of your stress energy tensor with energy density, the space, the diagonal space part with pressure. You'll end up with these expressions anyway. Okay. Now, and the idea here is that if I want a phase of accelerated expansion, then what I need is for the equational state parameter. Okay. In other words, the pressure divided by the energy density to be something that is more negative than minus 1/3. Okay? So now if I take this scalar field here and look at my my pressure versus my energy density, and what I find is that if the potential is much larger than the kinetic term, then I will naturally have an equational state parameter for this scalar field, so p phi divided by rho phi, to be more or less equal to -1. Okay? So this is sort of like a dark energy, if you like the cosmological constant that we discussed earlier. And the cosmological constant leads to an accelerated phase of expansion. So if you have a scalar field, which you engineer so that it also has this equational state parameter satisfying something that's like -1, you will also get an exponential phase of expansion that is accelerated. Okay? So that's basically the very basic idea of how inflation works. The potential is, well, okay, there are tons of potentials people have explored in the literature. You could have fairly simple polynomial or kind of potentials like 5 to the 4th or m squared, phi squared, whatever. I don't know how many inflation models are out there. No point talking about them in any case. But the idea here is that, okay, so it's a basic picture. So your potential and your field lives up here initially, and where the potential dominates over the kinetic term, and so while your field is up here, it will be slowly moving because you don't have the kinetic term is small. Okay, and this phase here, when the field sort of slowly moves down, is called slow roll. Okay, because it's slowly rolling, and while slow roll is happening, you have inflating of space. Okay, that's the phase of exponential expansion. So and then. As the field moves down here, at some point the gradient of the potential becomes quite steep, and down here, once your field reaches up here, it will just roll down. Okay, and so here, once you get down to this point, your field will, the potential will be less than the kinetic term because you're picking up more kinetic energy, if you like, and that's basically when inflation ends. Okay, so you have exponential expansion here, it ends, and then you have this phase here, which is normally known as reheating, which basically allows you, which is the end of inflation, and then what you do there is to try to convert the energy that is initially in the scalar field into regular particles, okay? And then you can start radiation domination again. Okay, so here's another picture to show what's happening. So you have the slow roll happening over here, and then you have reheating over here. I'd say reheating is not very well understood. I guess there are people working on it, so I hope I'm not offending you. But anyway, the idea is that you you have reheating, and then you turn basically from the inflationary phase back into the radiation domination phase, and the rest of the thermal history that we described earlier can just keep going. Okay? So, and I think that's all I have to say. And yeah, and if you have questions, please ask, and thanks for your attention.